Cool. Perfect. Then maybe we can start now. So how many of you here care about privacy at all? Yeah? And how many of you are moving around your data from one place to another place? I think everyone, right? So I guess this talk will be really interesting for you. So I'm super happy to welcome Thomas from TLSNotary. So a huge round of applause for him.
Okay, hello everyone, thanks for having me here. So my name is Thomas, and the topic of the talk is TLSNotary, privacy preserving data portability for the web. So the topic is something? So the topic this goes by, or what TLSNotary is basically ZK-TLS or NPC-TLS, which is probably a better term. But yeah, before we'll have a look at what it is, let's first have a look at who is behind. So TLSNotary is a project inside Privacy and Scaling Explorations, and Privacy and Scaling Explorations is inside the Ethereum Foundation. So Privacy and Scaling Explorations, or PSE, is basically doing applied cryptography, and so we do a lot of research, but also production-ready implementations of cryptography and open source them, and then that way we hope for you developers to pick it up and build something awesome with it, right? And TLSNotary is one project inside of PSE. Okay, so let's have a look. What is TLSNotary? And let's have a look at what's the problem, let's recall how TLS works, and also let's have a look at the history of TLSNotary. So first, okay, what is the problem? The problem TLSNotary tries to solve. So today, when you connect to some website, so here in this example you're Alice and you're probably using HTTPS, so you get the website data. What you now cannot do is basically pass this data on to some other entity, in this case Bob, in some cryptographically verifiable way, right? So this is impossible nowadays. And you might want to do this because a lot of websites hold data about you, right? And so, for example, if you think of your government server and you would like to use data about you or your identity to basically forward it to some KYC provider, or you want to get some banking information about you to get some sort of loan, right? Even the Internet Archive is basically interested in that the people who are scraping the internet for them, that they provide proof of evidence that this is really a website which was online, right? Yeah, or maybe you just want to prove that you have some Steam in-game achievement. Yeah, so there are a lot of use cases for it, and currently the internet doesn't allow it. Okay, so let's have a look at how the internet basically works. So right above the TCP layer, which establishes the connection between several GPCs, you have the encryption layer, so to say, which is TLS, or transport layer security. And whenever you go to a website, basically it ensures two things. So the first thing is that you are connected to the right website, which the website claims to be. And the other thing is that that the traffic is basically encrypted, right? And these two things go by the name authenticity and confidentiality. And whenever you go to a website, basically you're using HTTPS, and the S is basically HTTP with TLS. So it's widely deployed. Right. So what you get is this authenticity and this confidentiality, but what you don't get is portability of your data, like I showed in the beginning, right? And this term in cryptography goes by non-repudiation, which basically means the website can just say, oh, well, we never sent this data out. It can always say, we didn't send it. And so Bob will never be able to really trust Alice if it's really data coming from the website. Right, so let's come to the brighter world of TLS with TLSNotary. So TLSNotary, in some sense, is an update to TLS. So you also have Alice basically visiting the website and operating a normal TLS connection. You also get authenticity and confidentiality, but now you get a lot more. So first, you have portability and privacy, right? So Alice has some sort of, is running this TLSNotary protocol with Bob. We will have a look at that later, how that works. But you will get the portability of your data. You will also have some sort of switch, or you can basically have influence on what you want to show about these data from the TLS connection. What's also pretty cool is that in this setup, this is a completely trustless protocol, right? So Alice basically proves, or does a proof about some data inside of this connection. And there are also some other pretty cool things. So for example, it's invisible to the website. The website thinks that you're just operating a normal TLS connection, so it doesn't even know that you're basically running TLSNotary behind. And also, yeah, it doesn't require any modifications to TLS, which is currently deployed, right? So, I mean, getting protocols like TLS deployed takes like 10 or 20 years probably to get some adoption. Yeah, but you don't need to change that. You can just use it. Okay, so, right, let's have a look at the history of TLSNotary. So TLSNotary is not a new protocol. It's been around for some time. I think it was 2012 or 13 when basically the idea was raised in the Bitcoin forum, and they originally they wanted to have basically a way of implementing a peer-to-peer exchange for Bitcoin, right? And they even had a paper and an implementation of that protocol, and they also had a browser extension which was called PageSigner. But then TLS 1.2 got out, and basically the TLS standard was changed. So PageSigner and the TLSNotary protocol had to be adopted at that time. Yeah. Then in 2019 there was a paper released which was called the DECO paper, which introduced a general purpose MPC into this topic of TLSNotary. And shortly afterwards, PSE got interested in this project and adopted it. And what we then did basically was proving how TLSNotary works, also using general purpose MPC, but also modifying it to make it usable under under real circumstances in the real world so that it works. Okay, and then in 2023 we had our alpha release. Okay, so now we've seen what it is. Let's have a look of how you might basically solve this problem of non-repudiation. Right? What are the ways you can do, and how does TLSNotary do it? Okay, so first, what's the reason for why this doesn't work? So you have to recall that TLSNotary basically in the encryption and decryption phase, so when you transmit traffic, you have symmetric keys, right? So these are the yellow keys here. And then you also see the problem basically because Alice and the website have the same keys, so Alice can make up traffic and fake it, even flip bits or completely invent the traffic and say that it was sent from the website, and there's just no way for Bob to differentiate this from being from the website basically sending it, right? Yeah. So, okay, what can we do to mitigate this? So the best thing to do is probably just to sign the data at the source, right? So when there's a website, it could basically just, or a server, it could basically just hash the traffic and sign it with some public or private key pair, and then send it over to Alice, and then Alice could simply forward it to Bob, and Bob would just have some way to query for the public key of the website and then just check the signature. Right, but yeah, this is, I mean, it's the best solution, and it's certainly the end game solution, but there are problems. So first, I mean, if you want to implement this, you would probably have to do it on the TLS and not at the application layer, so you would have to change TLS, which is hard. And also, yeah, you have to somehow, if you implement it on the application layer, then you have to somehow get the server to support it, right? And there are some disincentives to not do that, right? Because there are certain entities which, yeah, have an advantage of basically that they require that you require that they say yes to that, right? That they sign, yeah, you can do that what you want with our data. So there's a disincentive for that. You can use OAuth to implement that. So OAuth is basically an authorization protocol. So when there's some website which wants to know data about you from some other website, yeah, they can just send you there, and you would just check and say yes, okay, you can get that data. But this, yeah, comes with some privacy and censorship problems, because now the website, which is basically handing over the data, they know what you want to do without it, they know what you want to do with it, and if they don't like it, they might censor you, right? So you have to trust them in a way. And also, the website has to implement this protocol or support it. And yeah, what you can also do, there are some solutions to this problem which use a proxy approach, and that's basically when when basically you have an entity in between you and the server, and now they just basically forward your requests and forward all responses from the server, and they will just then record the traffic, right? So this would work. The website doesn't have to support it, but now you can easily block this, because now the proxy basically opens the connection to the server. It's always the same proxy. And you also have some privacy problems here, right? Even if the traffic is encrypted, so the proxy only sees encrypted traffic, and you prove stuff about that later, but the proxy still knows the website or the server you are now connected to. Yeah. The last thing basically is, in this proxy approach, you have network assumptions, which means that if you have an almighty prover, or Alice, for example, is now an internet service provider, so she has the ability to basically man in the middle of the connection and put herself in front of the proxy, then you run into security problems with this approach. Okay, so how does TLSNotary do it? TLSNotary uses a different approach, which is multi-party computation, right? So what is multi-party computation? That's basically, a big topic in cryptography. You have two or more parties. For TLSNotary, it's two parties. And they use this multi-party computation, which is they have private inputs, and they want to compute a public function on these private inputs, right? But their inputs stay private. And there are cryptographic ways to do that without having a third party, right? And this is exactly what TLSNotary does. So Alice and Bob are operating an MPC TLS connection. You see it here. And so Alice still connects to the website with TLS, and now only the client role is split between Alice and Bob, and they operate this MPC TLS connection together. Right, and then, so you are inside, you have this MPC TLS connection, you send your requests to the server, you get the response from the server. And after that, you basically, now Bob in this slide has basically some sort of knows about the traffic, and now there's a disclosure phase where Alice can basically open parts of the traffic she wants Bob to know, right? So because very often it's that you don't want to open the whole traffic, right? For example, we have a cookie here and we want to redact that. This is one reason, or sometimes also the information which is provided by the website is not fine or granular enough, and then you want to adapt or redact certain parts. And another thing you can do is basically do zero knowledge proofs on the content, right? So if you go to some server and they have some data about you, for example, your birthday, you might just want to prove that you're over 18, or for example, that you are not in the United States. So basically we support these two modes. Okay. So let's go back to TLS first in order to understand how TLSNotary works in the detail. So in TLS, you basically have two phases. The first one is the key exchange. So basically, nowadays you have elliptic curve Diffie-Hellman key exchange. You have public and private key pairs, and Alice and the server send their public keys to each other, and then you locally apply your private key to it, and then you arrive at it's called pre-master secret, which is then fed into some function which extends it. It's a pseudo-random function. And then at some point you arrive at the session key, right? So the session key is then used for symmetric encryption. So when you send ciphertext to the server, you encrypt and server also encrypts and you decrypt it when you get the response. So now in TLSNotary, basically you split this client role into these two, and it works like the verifier sends his public key to the prover, and the prover locally applies his public key to it and sends it to us. So they add it just edit and send it over to the server. And for the server, this looks just like some ordinary public key. So the server can derive his session secret, sends over his public key to the prover sends it or forwards it to the verifier, and now they locally apply their private key to it, and now they have a split, with basically a secret sharing of the pre-master secret. So this is only a secret sharing under elliptic curve point edition, which is a little bit problematic, because we want to use that later in some circuitry which isn't very friendly for that, so we convert it and use multi-party computation here for that to get from this elliptic curve sharing to the finite field sharing. And then in the end we just have an ordinary sharing of the client key between the prover and the verifier. And here you also see why TLSNotary works. So now the prover, or Alice, does no longer know the complete keys. So what she can't do now is basically make up traffic from the server or flip bits. That's impossible. She always has to work together with the verifier for sending out requests and for decrypting responses. And that's exactly what we'll do. So if you want to send a request, you have the encryption here, and I've used here the example of AES GCM, which is basically a very famous cipher in TLS. So it's AES in counter mode and a G-hash MAC added to it. So now the prover has his key share and the plaintext as an input, and the verifier uses his key share, and then they in MPC basically encrypt the plaintext to the ciphertext. The verifier and the prover get the ciphertext, they compute the tag for it, and then the prover can basically send the encrypted ciphertext to the server. Decryption is pretty similar. So now you have the server send you a response. You both, prover and verifier, cooperate to check that that's the right tag, and then they decrypt. So now the plaintext is of course only returned to the prover, right? And then there's another step which is not on this slide, which is that the prover basically proves to the verifier that this plaintext re-encrypts back to the ciphertext. And this way we create a commitment to the plaintext. Right. Okay, so far there was only server, prover, verifier. So why is this project called TLSNotary? So, like, if you remember, I talked about these two phases, having the TLS or MPC TLS phase, and then after that you have this disclosure phase. So now you run a little bit into problems, because if you want to do that with several verifiers, you always have to repeat the whole process, which is quite resource intensive, right? So we have a designated verifier protocol. So there's no way basically for other verifiers to publicly verify that. So you always have to repeat the whole process. And this might be problematic in some resource constrained environments. Like, for example, think of this thing here, verifier running in an on-chain contract, for example. Then it won't be able to operate this MPC TLS connection. So what we can do is we separate the MPC TLS from the disclosure phase and introduce a new party, which is called the notary. And the notary's task is basically to just operate this MPC and TLS connection together with the prover. And then in the end, the notary will basically sign an attestation of the traffic and send it to the prover. And then after that, the prover can use this and present it to different verifiers. And the nice thing is now it's reusable. So this attestation, you can use that for verifier A and use different openings in the disclosure phase than use when you use it with verifier B. Genau. Right, but one important thing is now we don't have a trustless protocol anymore, right? So now we introduce a trust assumption here, which is that the verifier has to trust the notary. It has to trust that the notary and prover behaved honestly, that they didn't collude, especially that the notary didn't leak the session keys to the prover. Okay, I've now talked a little bit about how it works and so on. Let's have a look at real-world applications. So we have written this open source and in Rust. So we have Rust library on GitHub which implements all of this. But we don't only have library, we also have server and client implementations. So we have a fully fledged server implementation. We also have documentation on that topic available. We need to improve that documentation a bit on the cryptography part, but that will come. We also have some tooling around that. We have a proof visualizer, which allows you to inspect and debug these proofs, which the notary generated. And we had to write a lot of cryptography code. And this code lives in its own library, which is called MPZ. And this, of course, is also open source. And at some point, this might evolve into an MPC library, which supports an MPC VM. Let's see. So one thing I wanted to especially highlight is our browser extension. This is just a Chrome extension, which allows you to use TLSNotary in the browser. It works like this. So when you go to some website and the extension is active, the extension basically logs the requests which are going out, and at some point when you have a request which you want to notarize, you can click it and then hit a button, and then the extension replays the request, and it's notarized. So one thing to make it work is one thing we had to ensure is, so inside the browser extension you don't have access to the raw TCP traffic. That's technically possible. So it goes to some WebSocket proxy first. We plan to support some plugin system for this extension. What does that mean? So if you think about it, the verifier is the party who basically knows the most about what the verifier wants to see in the end. So the plugin system is a way for the verifier to write a plugin and then hand it over to the prover. And now the prover can just use this plugin and is basically driven through the notarization process, so that it basically generates exactly what the verifier needs in the end, which is pretty cool. And coming back to the beginning, you see there are a lot of use cases, especially in identity, also financial and social areas. And I mean, we're excited to see what you're going to build with it. The nice thing is that you have to think about it like the data now becomes composable, right? You don't have to have the agreement from the web server. Right? You can just build stuff with it. So one example I want to highlight, especially here because it's a blockchain conference, is the ZK P2P application. So what is ZK P2P? ZK P2P is basically a peer-to-peer exchange or fiat to crypto on-ramps. So nowadays the problem is that when you want to be onboarded into the crypto space, you first have to go to some centralized exchange. And ZK P2P basically is a way to crowdsource this. So how does it work? You have a seller, which in this example wants to sell some Ether, and puts it into a smart contract. And then you have a buyer who wants to buy Ether, and he now uses an off-chain payment protocol. For example, ZK P2P uses, I think, Venmo, and in Europe it's Revolut. And then you do the off-chain payment, and you then use TLSNotary to generate a proof of this off-chain payment, basically, right? And then you can put that as an input to the smart contract, and the smart contract releases the assets. Okay, so where are we now? So this is the roadmap we currently have in our heads. So first thing, we need to improve the performance of the protocol, and by that I mean we need to improve the traffic size you can notarize. So at the moment we are in the 2 digits kilobyte range, but we definitely want to get into the megabyte range, and for that we have to switch out our proving systems. So currently it works with garbled circuits, but we want to support bowly proving, which is protocols called Consilver. We want to support on-chain verifiers. There is the problem that you have to do this whole third chain validation, right, which is quite computation intensive. And this is probably a problem for smart contracts. So what we want to do is we want to use some ZK proofs of the third chain, but we need to work on this. At some point, we surely want to support TLS 1.3. So currently, we only support 1.2, but this will change. And we need to improve our tooling. So the extension and the plugin system will get better. We also want to improve the tooling for parsing the traffic, right? So TLS or HTTP supports arbitrary formats you can send, and if you want to disclose parts of it, you will basically need a way to parse different formats, and we need to improve our tooling for that. And in the end, we are also thinking about supporting n-party protocol so that you have several notaries for one session in order to make the collusion even harder. And just let's see what else comes to that. Yeah, thanks. That's it.
We have a little bit of time, so maybe one or two questions, quick questions, if anyone has. Yeah.
If the notary is trusted, why doesn't the notary make the request in the first place?
Yeah, that is basically the proxy approach, right?
Yeah.
Let's go back to this. Where was it? That. So if the proxy does the approach, you have a reduced privacy now, because now when the proxy does the approach, for example, he knows the website you're connecting to. So in TLSNotary, the notary isn't even aware of the website which you're connected.
Oh, I see.
It only sees encrypted traffic and doesn't even know the website. And there are also some security problems considering network assumptions. If you have an almighty ISP, basically your man in the middle is the connection. I mean, the proxy approach is a valid approach, right? But it depends on your use case.
So the notary is trusted not to collude with the website.
So the verifier has to trust the notary that it doesn't collude with the prover.
Prover.
Mm-hmm.
Yeah, my question was about the extension, the way you are implementing it right now. Doesn't it really introduce another proxy kind of situation with the WebSockets and everything kind of compromising again?
I mean, the end game is probably to get that into the browser, right? It's I mean, you have this WebSocket proxy at the moment, this is true, but we try to get that at some point really into the browsers, yeah. I mean, the super end game is signatures, right? But between that, we try to get that into the browsers natively.
Any other questions? Perfect. If not, then thanks a lot, Paul, for your amazing talk.